Until now, we've been dealing with force and Newton's laws in essentially one dimension. We've been, things are going up and down or forward and backwards. And now let's expand that a little bit and go back to some of the vectors that I introduced when we did two-dimensional projectile motion and use the vectors to study Newton's laws in two dimensions. So let's say I have the ground. Let me draw the ground in green. This is the ground. I want to take up too much space, and let's assume that that is flat. And I have a block on the ground. Well, you know what? Let's say this is ice, because for now that looks like, well, this is ice colored. I don't want to deal with friction. We'll deal with friction soon enough. So let's say that I'm on a frozen lake that has very little friction, and on top of that I have another block of ice. I have another block of ice. So it's ice on ice. So ice on ice has, at least in our world that we deal with every day, it's probably, and let's say there's even oil on top of the ice. So it's zero friction. And let's say that I'm pulling the ice. And, if I told you that I was pulling the ice straight to the right, that would be an easy problem. We could do F equals ma, and you could figure out, if I told you its force, we could figure out how fast I'm accelerating the block. But what I'm going to do is something that's maybe a little bit more realistic. Let's say I have something hooked into the ice, and then I have a string, and then that string is actually going up at an angle. And then I'm holding, this is me. Well, you get the point. So, and this is realistic, because if I was pulling a block of ice, it's unlikely that I'd be pulling it straight horizontally. I'd probably, the string would be lifted a little bit. And let's say that the angle that the string makes with the horizontal, so the angle with the horizontal, so this is the horizontal, right? The angle that string, let me switch colors, because not everything is ice. The angle it makes is 30 degrees. Let's say that the block of ice is, I don't know. Let's say it's a heavy block of ice. Let's say it's 50 kilograms. 50 kilograms. That's heavy. That's over 100 pounds. So 50 kilogram block of ice. And let's say that I'm pulling with a force. So let me draw my force, and this will be a vector. So I'm pulling in this direction, right? I'm pulling in this direction. And it's a vector, right? Because a force has both a magnitude and a direction. That's what makes it a vector. And so this is the direction we said, 30 degrees up from the horizontal. And let's say the force that I'm pulling on the string, and this could also be considered the tension on the string, and we're going to be doing some tension problems in a few videos. But the tension on the string, or the force that I'm pulling on it with, let's say that is, oh, I don't know. Let me make up a number. Let me say 10 newtons. That might be a realistic number. I'm assuming that I think I'm stronger than that. But let's just say it's 10 newtons. So how fast is this block going to accelerate? And so the question is, well, one, what direction will it accelerate in? And what direction will it not accelerate in? But let's just figure this out. So if we want to figure out how fast will it accelerate to the right, or in the direction, not that I'm pulling, because I'm pulling upwards, right? And as you could probably guess, 10 newtons isn't going to pull a 50 kilogram block upwards. But let's say I want to pull it, I want to figure out its speed to the right. So what we do is we break up this force vector into its two components, into its upward component and into its horizontal component. And this is just like what we did with the velocity vectors when we did two-dimensional projectile motion. And the way I think about it is I think of it like the sides of a rectangle or the sides of a triangle. If you just, let me pick a better color. So its horizontal magnitude is just going to be kind of, if you imagined this vector in an xy coordinate plane, it would be essentially the x, the magnitude, the x value. If this was the point, if this was the, if this was 10 away at a 30-degree angle, this value right here would be its x value, and then the y value would be this. And another way you could think about it, I could have drawn this y value here, and they would make up a triangle, right? Actually, that might not be clear. Let me draw it here. I could have drawn the y value here and make up a triangle. You could think of it either way. Sometimes you'll see someone, they'll have all the vectors starting at the same point, and sometimes you'll see this vector pushed over here so that you can kind of see that it forms a triangle. So let's figure out what the sides of this triangle are. So we want to figure out the horizontal component. So the horizontal component is this side, right? And let's go back to our trigonometry. So SOHCAHTOA. We know what? We know this 10 newtons. The length of this vector is 10 newtons, or the magnitude. And that's the hypotenuse of this triangle. And we know, and what we want to figure out is the adjacent side, right? Because we have this angle. So we know the hypotenuse. We want to figure out the adjacent. What do we use? We use cosine, ka. Cosine is adjacent over hypotenuse. So that tells us that the cosine of 30 degrees, is equal to the adjacent side. So let's say that's the force in the x direction. That's the adjacent side. Force sub x over the hypotenuse over 10. We can multiply both sides by 10, and you get the force in the x direction is equal to 10 cosine of 30 degrees. And let's figure out what that is. Well, if you know your 30, 60, 90 triangles, you could figure it out. It's actually square root of 3 over 2 cosine of 30 degrees. But I'll take out the handy calculator. Oh, that's not the right calculator. I wanted to use the other one. Actually, let's just stick around with this one, because we know this is a 30, 60, 90 triangle. And if this is, you could use a calculator to figure it out, but I don't have the calculator handy just now, so we'll do it by hand. So the cosine of 30 degrees is, if you haven't memorized it, it's square root of 3 over 2. So the force in the x direction is equal to 10 times the square root of 3 over 2, which equals 5 square roots of 3, right? 10 divided by 2. Force in the x direction. Newtons. So now we can figure out its acceleration in the x direction, because force in the x direction is equal to mass times acceleration in the x direction. So if we divide both sides by the mass, we get the acceleration in the x direction is the force in the x direction divided by the mass. And that equals 5 square roots of 3 newtons, 5 square root of 3 newtons, over 50 kilograms. Over 50 kilograms. And we know that the units are right, because we're dealing with newtons, and not kilonewtons or something, and we're dealing with kilograms, not grams or decagrams or something. And so this turns into, let's see, 1 over 10, right? So it's square root of 3 over 10 meters per second squared is the acceleration in the rightward direction, or in the x direction, we could say. And so what else is going to happen to the block? I mean, as we see, I'm pulling at an angle, so there is an upward component. So am I lifting the block somehow? Am I picking up this portion of the block? Well, let's figure that out. Let me see if I can. Oh, no. Let me see if I can clean this up a little bit. Okay, that should give me enough space. Okay, so similarly, we want to figure out the length of this vector right here, right? The force in the y direction, and we could use the same logic. That's going to be the sine, right? The sine of 30 degrees is equal to opposite over hypotenuse is equal to force in the y direction divided by the hypotenuse, 10. So the force in the y direction is equal to 10 sine of 30. Sine of 30 degrees is easier. That's 1/2, in case you haven't memorized it. So that's 1/2. This is 1/2 times 10. So the force in the y direction is equal to 10 newtons. So I'm essentially pulling up on this point in the block of ice at 10 newtons. So is the block of ice going to move up? Think about it a little bit. Maybe you want to pause it. Well, what's the force in the downward direction at that of the block of ice? Well, the force in the block downward direction. Actually, I should probably assume that I'm somehow hooked to the middle of it. Maybe this is the center mass, but I don't want to get too technical right now. But as a whole, because maybe I could tilt it a little bit. I might be able to tilt it, but I won't go into that much. But the force downward, what's the force of gravity on this block? Well, it's 50 kilograms times 9.8, or roughly 10 meters per second squared, right? So the downward force of gravity is something like 500 newtons. 500 newtons, gravity's pushing down. And my upward force is only, it's 5 newtons, sorry. My upward force is only 5 newtons. So still the net force on this block in the y direction is still downwards, and it's really the ice is supporting most of the weight of this block. And what I'm doing is really, maybe I'm lessening that already small friction a little bit. So I'm really not moving the block at all in the up direction. I'm just pulling it in the x direction, and I'm running out of time. So I'll see you all in the next video.